the talk. So in the first section, which is an introduction, I will introduce the main object of study, which is holomorphic curves in almost complex manifolds. Then in section 2, I will collect some tools from analysis that we will need for the main theorem that I will state in this talk. So this will be just treated as a black box section. So I will not really get into the proofs of any of these analytical estimates. Then section 3 contains the main result statement. And before that, there is some setup and notations required to state the main result. Section 4 is a sketch of the proof. The proof is somewhat long, so I will focus on one particular step, which is quite easy to explain, and the rest I will try to illustrate more or less through some suggestive pictures. Then the last section is about an application which is in progress. So this is the last section will have, I guess, even fewer details than the previous ones, because this is very much in progress, and I have not also filled in all the details. So, okay, so yeah, so our basic object of study is a compact almost complex manifold X, J. So what this means is that X is a compact smooth manifold, and J is an almost complex structure, which means that it's an endomorphism of the tangent bundle which squares to -1. So what this means is that the tangent bundle of X acquires a complex vector bundle structure with J acting as multiplication by the square root of -1. Okay. Also, for the rest of this talk, we'll endow Tx with a unitary metric. So in other words, it's a Riemannian metric which respects J. And I'm not going to explicitly give this metric a name. Just imagine that this is there in the background. Okay. So now let's fix a non-negative integer G and a second homology class in X called beta. So G you should think of as the genus of a Riemann surface. So now I'm going to consider the following moduli space, which consists of the following objects. So an object in this moduli space is a holomorphic map from a Riemann surface sigma of genus G to our almost complex manifold X. So being holomorphic is just saying that du is complex linear, which makes sense because sigma is a Riemann surface and Tx has a complex vector bundle structure. And saying that this map is in class beta means that the fundamental class of sigma pushes forward to beta. So this is just some kind of topological data on the map. And we look at all such maps up to an obvious notion of isomorphism, namely sigma ju is isomorphic to sigma prime j prime u prime if there is a biholomorphism from sigma to sigma prime which switches u to u prime. And we call this moduli space of all such curves up to isomorphism as mg of xj beta. Okay, so so now I'm going to very quickly zip through some background about why this moduli space might be interesting. And so we can do
Mohan,
some.
just sorry to butt in, but you're not keeping any marking information of fundamental group or anything here, right?
No. This is just curves equipped with a map on them up to isomorphism.
So which means that, I mean, just to confirm, so if the target is already a Riemann surface of the same genus, then you're going to get moduli space out of this.
Yeah. So I mean, moduli space of branched covers, you could say, of that Riemann.
Yeah, no, I mean, if the genus is the same, I'm saying if the genus is the same, then you just get the usual moduli space back, right?
Well, I mean, the target is a fixed Riemann surface, so you won't be able to have a map from a different Riemann surface to this one, right, of the same genus.
Oh, yeah, that's right.
So yeah, so if you think the target is a point, then you get the ordinary moduli space.
Okay, fine, fair enough.
Yeah. Okay. So yeah, so we can do some deformation theory arguments to see that we can compute the Zariski tangent space of this moduli space and the obstruction space. And the difference of these two can be computed using the Riemann-Roch theorem. So I'm deliberately not giving too many details here, as this is just supposed to be a motivation and not that much of the focus of the talk. So using Riemann-Roch theorem, we find that the expected dimension of the moduli space, which is to say the dimension of the tangent, Zariski tangent space minus the obstruction space, is given by this formula. nu equal to n minus 3 times.
Sorry, mgx. So the Riemann surface structure on X is fixed, right?
So X is an almost complex manifold. So it's possibly higher dimensional, but that is fixed.
Oh, X is, okay. So
X is the target.
Okay. Sorry. So the Riemann surface is varies in Ng in your
Yes.
Ng.
Correct.
Yeah. Okay.
Yeah. So I mean that's what is the source of this 3g minus type term appearing in nu. And the other term is just a Riemann-Roch term, n times 1 minus g plus c1 of tx paired with beta. Okay. So an immediate example that is of interest is suppose X is a Calabi-Yau threefold. So this is to say it's a three-dimensional complex projective variety with the canonical bundle being trivial. So in particular, n is 3 and c1 of tx is 0. So then you can just plug in this stuff into this formula and see that nu is always 0. So in other words, the moduli space is always expected to be of dimension 0. Okay, this means the Zariski tangent space and the obstruction space have the same dimension. So in any case, given this dimension count, we might try to do the following. If the dimension of this moduli space is 0, then we might ask how many points are there in this moduli space, because you might think the moduli space is just a discrete set of points. So we could just count those number of points. If not, if it's positive dimensional, then maybe by placing some constraints on this moduli space, we can reduce the collection of curves to some finite set which could be counted. So these conditions could be something like passing through a certain given point in the target X, or being tangent to a given line in the target X, etc.
One more sanity check. So what happens if you take, say, instead of taking a Calabi-Yau threefold, you take, say, a K3 surface? So your first term is negative, right? But you still have maps of P1 into K3, right? You do have rational curves.
Yes. So yeah, which is why this is just a virtual dimension. So I mean, this is not or an expected dimension. That actually means that in the deformation obstruction complex, I mean, the obstruction has a bigger size than the deformations. It doesn't mean curves don't exist.
Okay.
Yeah. So this expected dimension is to be taken with a grain of salt, meaning that it does not necessarily tell us the dimension of the moduli space itself. So it just tells us what the dimension should be from the perspective of deformation theory. So in some sense, if everything were transversely cut out, then it would mean the moduli space is empty if nu is less than 0.
Nice. Thanks. Yeah.
Okay. So the guiding principle that we have is that counting points of this moduli space mg of xj beta with appropriate incidence constraints can yield numerical invariants of x comma j. So an example would be the following. If you look at the space of all conics in P2, so all conics are rational. So that means we have fixed genus equal to 0. The homology class is 2 times the class of a line, and x, of course, is P2. Then the number of, so of course, the family of conics in P2 is some big family. But if we fix 5 generic points in P2, then there is a unique conic passing through these 5 points. And so this is an example of such a numerical invariant. Namely, we place these 5-point constraints, and then we have only one conic passing through this. Similarly, you can ask something about rational cubics in P2, and it turns out then you need to fix 8-point constraints. And this time there's not a unique cubic, but there are in fact 12 cubics. So that's another example of such a numerical invariant. So those were just 2 examples of what such a numerical invariant might look like. Okay. So, but now we have an actual problem when we try to define this counting. So counting requires the moduli spaces to be compact. That is, even if they are of dimension 0, an isolated set of points cannot be counted unless it's a finite set. So we need compactness of the moduli space. And this can fail in general. So here's a sketch to, here's a picture to illustrate how this could fail. So first, let me explain what is going on in the picture. So this is a picture of the blow up of P2 at the origin. And this map pi is the blowdown map to P2. And here I've shown the affine chart C2 sitting inside of the blow up. And here the vertical line that that the mouse pointer is at is the exceptional curve E. So it's a portion of the exceptional curve. So in this real picture, E is supposed to close up and look like a circle, but I'm just showing you a segment of it. And Now, you notice that by the definition of the blow-up, all these directions passing through the origin, which are shown by this rainbow color of straight lines passing through the origin, each of them transforms to some line in the blow-up, and each of them meets the exceptional curve at a different point. So now let's look at this black line parallel to the red line in the base. So L is the black line. If I take its pre-image L tilde, then this is a curve that lies in a certain specific class in the blow-up. And of course, this class will remain the same if I just move L continuously in the base. So now you can see that as L approaches the red line while staying parallel to it, this L tilde will actually approach a curve that is not anymore smooth. It will approach a curve that looks like the union of the red line in the blow-up and the exceptional curve in the blow-up. So this is something which looks like a nodal curve. So as an ordinary nodal singularity forms at the place where the red line meets the exceptional curve. And so this is an example of a sequence which will not have any convergent subsequence converging to a smooth limit. So what this is telling us is that the moduli space is not in general going to be compact, but we actually would, and it also gives us some idea of how it fails to be compact. Tells us that we should probably add some kinds of singular curves to the moduli space in order to make it compact. One more thing I would like to point out is that if you take a small neighborhood of the origin in C2 and you remove that, then the portion of the black line L that lies outside of that, as it tends to the red line, it just limits to the strict transform of the red line, while the portion near the origin is what spreads out and wraps around the exceptional curve. So you see that a very small portion of the black line actually maps onto the entire exceptional curve. So this is to say that the derivative of this map is actually blowing up near the origin. So this is again a feature we will see when we actually see the proof of the compactness theorem.
So you said that you can compactify, or what exactly was the point of that? I mean.
So far we have not seen exactly that we can compactify, but this is giving us a suggestion that maybe adding certain kinds of singular curves which lie in the same homology class will give us a compactification.
Okay. Fine.
Yeah, so I mean, this was just an example of failure of compactness and sort of a suggestion on what could be added to compactify it. So below I give you the actual answer for what the compactification is. So the solution to this compactness problem was given by Gromov in his seminal 1985 paper, which introduced holomorphic curves in symplectic geometry. And it was further refined by Kontsevich in his 1994 paper, where he showed that this compactification actually is Hausdorff, and which is again quite an important property. And it turns out this was missed by Gromov in his 1985 paper. So this theorem is called Gromov's compactness theorem, and it says the following. So firstly, we cannot take any arbitrary almost complex structure J, but it has to be of a special kind. And this I will proceed to describe now. So suppose that X has a symplectic form omega. So let me quickly remind you that this means that this is a 2 form, which is closed and is everywhere non-degenerate. And this can also be restated as saying the top exterior power of omega is nowhere vanishing. So we say that omega tames the almost complex structure J if omega of v comma jv is positive for every tangent vector v. So that's this condition that I've written here. I've written it as omega of v comma jv is bigger than or equal to constant times v squared, which is the same thing. So then we consider the following moduli space. It's called the moduli space of stable holomorphic maps of genus G in class beta. And what that means is the following. So again, this looks like a map from a Riemann surface to X, except that now our domain may not be a Riemann surface, but it could be what's called a pre-stable curve of genus G. So in other words, this is a projective connected curve, which has at worst nodal singularities. And if we smooth out the nodes, that is, we replace each of those nodes by a small annulus, that is, we do a sort of connected sum at each of the nodes, then we get a curve of genus G. That's what it means to say that the pre-stable curve has arithmetic genus G. U is a holomorphic map from this curve into X. This just means that on each irreducible component, which is a smooth Riemann surface, the the map U is holomorphic. It lies in class beta, again means that the total class, if you add up the push forward of the fundamental class of each irreducible component, that should add up to the given class beta. And stability, this is a very important condition which was noticed by Kuntsevich and missed by Gromov's original paper. This condition is required to make the moduli space Hausdorff, and this condition says that the automorphism group of sigma JU is actually finite. So in other words, the space of the set of biholomorphisms of sigma which preserve the map U is actually finite. So that's what the condition of stability says. Again, we have an obvious notion of isomorphism between two such stable maps, and we consider the moduli space of all such stable maps up to isomorphism, and call this mg bar of xj beta. And the compactness theorem is that this space is actually a compact Hausdorff space. Okay, so maybe let me just say one word about
yeah. Can you just one more time just say what stability is here? I mean,
yeah. So
does it have stuff to do with bubbling of spheres or something? Is that a cause of instability? What exactly is going on? Yeah.
So stability is saying that so basically yeah. So let me maybe just draw a picture here. So if you have a sphere with a map to X, then you can of course form another curve which is just given by adding another sphere to it, which just maps by a constant.
Right.
So you don't want to include such things. You want to include constant components only when it's absolutely necessary. So for example, this would be a case where you actually want to introduce a constant component. So you have three independent spheres mapping non-constantly, and then you have this constant sphere that sort of mediates between them. The only reason we need this constant sphere is that we are allowing only ordinary nodal singularities. And so we need this thing in between in order to make sure that we don't have a triple node.
I see.
So stability. So stability in genus 0 basically just means that any constant component must be attached at least 3 points to other components, so that there are no automorphisms left over.
Okay, fine. Thanks. Yeah. Okay.
Sorry, I thought so. I don't see where the taming form figures in the statement.
Oh, so the statement, yeah. So that's actually very interesting, because it's just that if there exists a taming form, then we have compactness. So I've not yet shown you how exactly omega gives us compactness, but the statement itself is just about a moduli space which depends a priori only on J. It's just that
I thought
having this additional.
If X was stable, there is always a taming form, right? Isn't that true? If X was compact.
No, I don't think that's true. I mean, if X is, I mean, in all algebraic examples, I mean, we think of them as projective varieties or Kähler manifolds. So sort of this comes together with a symplectic form. But in general, there's no reason for this to be the case, that we have an omega which tames this. Because I mean, finding a symplectic form is somewhat complicated. I mean, it's not just an algebraic topological property.
So I see. So if you are in the symplectic category, you would start from the symplectic form. So then this, then you talk about then the J becomes a choice, but here you're going the other way.
Yeah.
Okay. So that may not exist.
Yes.
So, but once such a omega exists, it's pretty much irrelevant for. Then what you're saying is that then it's exactly like an algebraic geometry.
Exactly.
Okay.
Yeah, it's just that somehow this omega being in the background somehow miraculously gives us compactness.
Okay.
That's what I want to maybe explain in the later part of the talk, when I talk about the compactness theorem in more detail. Okay, so now so using this compactness, we can actually.
So, Mohan, sorry to again interrupt, but when you're looking at it, your target is now just a symplectic manifold. What will be the topology that you're looking at? I mean, of spaces. So, in order to ensure, say, that a sequence, I mean, what does it mean for a sequence of almost holomorphic curves to converge to another almost holomorphic curve?
Yeah. So this is so basically this is particularly easy to describe. Let's say if I'm in slightly so firstly, it's easy to describe what it means for a sequence of maps from a parameterized curve to X to converge, right? If I have a sequence of maps from P1 to X, then
sure.
I can certainly see what it means for it to converge. So you should think about this as, if I have a sequence of curves from P1, then I allow myself to reparameterize these and then ask if this sequence converges. That would then say that as an abstract holomorphic curve of genus 0, the sequence converges. That is, when we allow these reparameterizations as well, then that would be the topology on this moduli space. That's what we do in order to forget the parameterization. Does that make sense?
Yeah, I understand. Okay.
So I mean, the definition is going to be a little more complicated when we actually allow bubbles to form and nodal curves to appear. So here, what you'll have to do is you'll take a target curve, which is the limiting curve, which is nodal, and then you will sort of, away from the nodes, you will be able to see that this is, that is a large open subset of this nodal curve is actually isomorphic to a large open subset of the non-nodal sequence. And then on this open set, you will try to compare the two maps in order to see what the notion of convergence is.
So it's basically, instead of parameterized, it's some kind of geometric convergence.
Yeah, but except that it's not really just convergence of the images, because the parameterization also matters to some extent. Because, for example, branched covers of embedded curves are considered as something more complicated than simply an embedded curve with a multiplicity, because we kind of keep track of where the branch points are also.
Yeah. Thanks.
Okay.
Yeah, presumably, you could have, say, a sequence of curves of some genus, and then the limiting guy is a lower genus curve which is covered some finitely many times.
Yes, that can certainly happen. Yeah. So so from the stable map point of view, it would still be a stable map of the same genus. It's just that its domain is the thing that now is a witness to the fact that it has genus G. The image actually looks maybe of lower genus. Okay. So now our earlier guiding principle tells us that when we have compactness, we can define these numerical invariants for X, omega, and J, and these are called the Gromov-Witten invariants. So so it's a very remarkable fact that the Gromov-Witten invariants actually depend only upon omega. That is, if we fix an omega and we take any J which is tamed by it, we will get the same Gromov-Witten invariants. Not only that, we can actually even vary omega in a continuous family. That is, Gromov-Witten invariants only depend upon the deformation class of omega. So if you have a one parameter family of symplectic forms, then again the Gromov-Witten invariant does not change. So so now
this is some softness theorem that you're talking about. Basically some kind of algebraic topological information determines. Omega is going to give you an almost complex structure, right? So presumably omega in some particular, and almost complex structures are classified by some algebraic topology information, right?
Yeah. Though so I don't know how we would sort of pick out those algebraic topological data which are tamed by a symplectic form. I'm not completely sure.
Okay. That's a harder problem. Yeah, sure. Thanks.
Yeah. So one last question. So if you have a complex manifold even, which is not Kählerizable, then compactness might fail. Right?
Yeah, it could fail. Yes.
Okay.
Yeah. Okay. Thanks. So now the usual proofs of Gromov compactness show sequential compactness. That is, we take some sequence of curves and then we try to find a convergent subsequence. And as usual, whenever you have a sequence of maps and you're trying to find a convergent subsequence, the idea is to somehow try and use Arzelà-Ascoli theorem. So try to see if the gradient of these maps is uniformly bounded, and if so, then try to extract a subsequence. And as we saw in the blow up example earlier, the gradient might actually blow up at some points. And so this proof will require some more work. So I'm actually going to present a quantitative version of this theorem in the genus 0 case. And towards the end of the talk, I'll also outline an application of this to the study of Gromov-Witten invariants. So this is something which is in progress. So it will just be a very rough sketch. Okay. So now I need to quickly recall some tools from analysis that we will need. And these things I will not be proving. We just sort of use them as a black box in the rest of the talk. So the first thing we need is the following. If we have a Riemann surface sigma comma j, then we can define for any smooth map u from sigma to x the notion of its energy. So this energy is defined in the following way. So fix h to be any conformal metric on sigma. So what this means is that if sigma has a local holomorphic coordinate z, then mod of dz squared is a metric, a flat metric on that coordinate neighborhood. If I multiply this by any positive function, I get what's called a conformal metric. And this is the definition of a conformal metric in local coordinates. So any two conformal metrics will actually differ by multiplication by a positive function. So pick such a metric h, and then define the energy of u to be half of this integral. The integral is a mod of du squared times the volume form of the metric. So both of these terms have an h dependence on them, but you can check that the product of these two actually is independent of h, because if I change h by a conformal factor, then these two factors will actually change in exactly opposite ways so as to compensate, and this product will remain a well-defined differential form to be integrated on sigma. So that's what's called the energy of a smooth map. And what this tells me is that in local coordinates, I can just compute this by taking a flat metric on a local patch and just writing down the integral of du squared with respect to the standard volume form dz wedge dz bar times I over 2.
So basically your u actually, I mean, EU actually now is going to give you a function on the moduli space of sigma. Is that correct? I mean, that,
yeah, so actually we will essentially so we will just see below. I mean, so point 1 is exactly going to tell us that if omega times j, then in fact the energy is uniformly bounded on our moduli space. So this is so the energy is some sort of analytical quantity which is useful to try to apply this Arzelà-Ascoli type argument, but the tameness will tell us that it's actually related to this topological quantity, namely the pairing of the class of the curve with the class of omega. So, okay. So the first statement is that if omega times j, then the energy of u is smaller than or equal to a constant times the integral of omega along the map u. And this is just a consequence of, it's a direct consequence of tameness. So what we need to just notice is that if I take V to be anything in the tangent space of the image of U, so I'm just being kind of informal here, then the tangent space of the image of U is spanned by V and JV because the image is some pseudo-holomorphic submanifold. So omega of V comma JV we know is bigger than or equal to a constant times V squared. And now this is the infinitesimal contribution to the energy, and this is the contribution to the right hand side. And so this tells us that this pointwise inequality actually integrates out to this integral inequality. Okay, so now the second analytical fact we need, which is probably the most important for this talk, is something called the mean value estimate. And this should remind you of the mean value inequality for subharmonic functions. So what this is telling us is that if U is a holomorphic map defined on a ball of radius r, so this is a ball of radius r within the complex plane, and its energy is smaller than or equal to a certain threshold amount, which I'll call h bar, sort of to remind you of minimum energy. So if it's smaller than or equal to h bar, then then the derivative of u at the center of the ball is controlled by 1 over, so derivative squared is controlled by 1 over r squared times the energy on this ball. So taking square roots, what this is telling us is that du at the origin is controlled by 1 over r times the square root of the energy on this ball. So
this is some kind of Schwarz lemma?
So the proof at least doesn't look quite like that. The proof resembles more something like the mean value inequality for subharmonic functions. So we actually prove something like this thing is bigger than equal to some constant times its square, and then I mean it's kind of an analytical proof. So yeah, I'm not completely sure if you could get it from the Schwarz lemma, but I mean there is a Schwarz lemma in this context as well, but yeah, I'm not completely sure what the relationship between this and that is.
Is there anything to prevent you from taking omega v jv to be the actual metric on X?
No, I mean, the only thing is that I only assume J is tamed by omega if J is compatible with omega, which is to say omega of JV, JW is omega of VW.
Because
then
you are using the metric to define E, right?
Yes, yes.
So if you, in fact, take the metric to be defined by omega, in fact, won't this be an equality? This
Yeah,
E,
it will be an equality. I mean, the only
that would be
technicality.
the Wertinger like thing, right? That
Exactly, exactly. So,
yeah.
I mean, the only issue is that if I define my V square to be omega of V JV, this may not be, I mean, this might not be a symmetric thing, as in we need to take this as the definition of the quadratic form, and from that we will get the metric as omega of JW plus omega of W JV half. So that would be the metric.
Right, okay.
Yeah. So, right. So now, and then the third fact, which is very important for us, is elliptic regularity. So this tells us that if we have a holomorphic map U, then local C1 bounds will give us local CK bounds for every K. So this is just sort of a general property of the Cauchy-Riemann equation. And in the ordinary complex analysis setting, we know how to derive this. This is just a consequence of the Cauchy integral formula, which tells us that if, I mean, I can write higher derivatives of U in terms of certain integral expressions in U. So if I have bounds on the first derivative of U, I can use that to get bounds on the higher derivatives as well. So in this case, the proof is a little more complicated because the Cauchy-Riemann equation we are looking at is slightly more nonlinear, but the spirit is the same. So I think in the interest of time, I will skip points 4 and 5 because in any case, the proof will not be given in so much detail so as to see exactly where they get used. So maybe let me go ahead to the next section. So maybe before that, let me stop. Are there any further questions before I get on with the main result? Okay, so I guess then I can proceed. So so first I will set up some notation before I can state the main result. So so now, given a stable tree T, so first let me tell you what a stable tree is. So a tree is just what you think it is, namely a graph with no cycles. A stable tree is one in which every internal vertex has at least degree 3. So an example is this picture that you see here on the left. So this is a tree which has 2 internal vertices which are marked in green, and each of them has degree 3. So given a stable tree T, we're going to form a space of genus 0 curves. This space will be called M sub T. And these are all equipped with what I will call a thick-thin decomposition modeled on T. So this is, to define this completely precisely, I can write down this family explicitly in coordinates as a subset of projective space, cross, and affine space. But I would prefer to just explain this suggestively using the picture that I have here. Namely that for every vertex, I will have a region which looks like a disk minus a few other disks. So look at the green regions in this picture. They all look like a disk minus a union of a disjoint union of 2 or more disks removed from it. Every pink region, which is corresponding to a terminal edge, is like capping off each of these disks that were removed by just other disks. And these red regions will be what I call necks. So they are, as in this picture, it represents an annulus. And this is an example which is somewhat a degenerate case of this, where the annulus has degenerated into 2 disks that meet each other at a point. So that's what a nodal singularity looks like. So this degenerates into this. So in other words, you should think of these as curves which are modeled on this graph roughly, namely that each vertex and edge corresponds to a region, and they are attached according to the incidence relations in the graph. And we allow for the annular region to shrink to a nodal region. And also we can endow these curves with a certain metric which reflects this this geometry that I've shown in this picture, namely that each green region looks about the size of a standard P1. Each pink region looks about the size of half, P1 with half the metric, and each red region looks like a superposition of two P1 metrics coming from two different sides on the annulus, which then degenerates when the annulus becomes infinitely long to just two disks attached at a point. So this is the family of curves that I am calling M sub t. And let's use some notation and call the universal family sitting over this as C sub t. So given a point P in M sub t, I will denote the curve corresponding to it by CPT. Okay, so so I'm intentionally being somewhat sketchy about the definition here, because the exact definition can be written down explicitly in coordinates, but I think the picture might be more illuminating. Okay, so now given this family of curves, I define a moduli space MT of xj beta to be the following. It consists of all pairs which consist of a point P in MT and a map F from the corresponding fiber CPT to X, and this F is required to be a holomorphic map in class beta. So this right now is just a set, but now I can answer the question of what is the topology on this very precisely. So remember that I told you that CT over MT, that the CT also carries a metric because it's explicitly embedded inside some PR cross CS by some coordinates. So CT carries some metric on it. So in particular, CT cross X carries a metric on it. And any such P comma F will give me a graph sitting inside CT cross X, right? The graph of the map F is a subset of CT cross X. And for two such pairs, PF and QG, I can take their graphs and measure the Hausdorff distance between these two graphs. That is what I take to be the metric on my boxed moduli space here. Okay, so so this is what I'm calling the Hausdorff distance. So I remind you that two close sets are said to be in Hausdorff distance less than epsilon if either lies within the epsilon neighborhood of the other. So
so you're using the background metric G in a fairly essential way to define this. But any metric which is in that same class will define the same topology.
Yes,
that's the point.
Yes. Yeah. So I mean, this topology is I mean, it's actually very natural, but I'm just using this very concrete definition to explain it here, because it's also useful from the point of view of understanding the analytical argument that will come next. So okay, so given this moduli space, I'm going to actually describe for you a subset of this, which I will also argue is compact. So this subset is given by three parameters: theta, eta, and lambda. And so this is the subset. So yeah, let me avoid saying its name because it has too many subscripts and superscripts. It's the subset of MT xj beta consisting of the following conditions. So the first condition is that P lies in M theta of T. So M theta of T is a certain compact subset of MT, which is given by the following condition. So each of these regions is abstractly an annulus, right? 0R cross S1. And this theta essentially controls how long this R is supposed to be. So in other words, how close we are to breaking to a set to a nodal curve like this.
So this is like the modulus of that annulus, is that right?
Exactly. So I mean, so this theta is telling us something. So as theta gets small, the modulus of the annulus gets big. So that's the thing you need to keep in mind. So in other words, you should think of M theta of T as sort of a neighborhood of the space of the most nodal curves sitting within the moduli space MT. So by most nodal, I just mean those for which every red region is degenerate, and M theta of T is just the set of curves which are sort of theta close to this most degenerate set of curves. Okay, so that's condition one. Condition
but all
two,
the source curves are actually smooth. You don't actually consider a degenerate.
Oh yeah, but I mean this is just some kind of, I mean, so you should see that the curve is just an abstract curve, but we have endowed it with this artificial thick thin decomposition. So I'm just saying that under this thick thin decomposition, those necks are long. I mean, there is no God-given thick-thin decomposition on these curves, right? Because these are genus 0 curves, and there's no way of sort of fixing an isomorphism with P1. It's more like I'm choosing a bunch of circles on the curve and declaring those more or less arbitrarily to be the boundaries of the thick and the thin regions.
Okay.
Mohan, so typically, is one more thing. I mean, so essentially, when you're using this expression thick-thin, typically this is used when you equip it with some sort of canonical metric, hyperbolic metric, and then there's this neck which becomes very long, less than the Margulis constant, etc., etc. So is that, I mean, is that an equivalent way of looking at this? I mean, where the plumbing, the places where you're doing this plumbing, that's the complex analytic thing. And if you equip this whole thing with a hyperbolic metric, then those little pink bubbles that you drew on the top, those are like going off to cusps, and the stuff in the middle are like long necks connecting to two bodies of this sphere.
Correct. So yeah, so I mean, yeah, so I'm the only reason I am avoiding that is because, I mean, these metrics are kind of very, very explicit, and you can write down formulas for them, while the hyperbolic metric is certainly canonical, but yeah, I mean, I personally just find it easier to work with these metrics since they are just some, rescaling the Fibonacci metric.
No, I'm just asking it because of my personal prejudice.
Sure. Yeah, I mean, so yeah, the analogy, so when I say thick-thin, I mean it in a very loose sense, that it's just an analogy with the hyperbolic thick-thin decomposition, but here it's just some sort of thing that I'm artificially imposing. It's not anything canonical like in the hyperbolic metric. Okay, so now that was the first condition. The second condition is that the gradient of f is bounded above by this constant lambda. So this is a C1 bound on this map f. And finally, the third condition is that every pink region has at least a minimum amount of energy. So this minimum amount is given by this constant eta. So each pink region has energy at least eta squared. Okay. So what does this, so you can see the second condition is obviously very important for showing compactness, because I will then be able to apply Arzelà-Ascoli. The first condition is also clearly important because then the set of points P themselves remain in a compact set. So what's the reason for the condition 3? So well, condition 3 certainly looks like a closed condition, but it also satisfies another important purpose, which is that when this red region degenerates to a node, then the resulting curve that we have is still going to give us a stable map. This is what I want to argue now based on condition number 3. And the reason for this is that each irreducible component, remember, each irreducible component is in bijection with its green region.
Okay, so Mohan, let me just sort of ask you one more thing quickly. So basically, the third condition, what it's preventing is that you don't want a chain of spheres between this top big sphere and the bottom big sphere. Is that the point of stability?
Exactly. So in other words, this is just saying that each vertex will, I mean, since we know that each vertex has at least 3 edges on it, if all 3 edges happen to be red edges, that is internal edges, then that's fine because stability allows us that. But if we don't have enough red edges, then we must have enough energy to ensure that the map is non-constant, and that's what the third condition is ensuring. Because each of these pink regions carries a minimum amount of energy. Okay, so that was also a very, very rough inwards argument for why this is compact. So more precisely, the way you would argue is using Arzelà-Ascoli and condition number 2. So condition number 2 will say that all the gradients are uniformly bounded, and so therefore you would be able to pass to a subsequence which converges, at least in C0, away from these nodes. But then to say that the limit is holomorphic, you will need to use the elliptic regularity statement I said earlier, namely that C1 bounds imply C infinity bounds. And so the convergence will in fact be in C infinity away from the nodes. And so therefore the limit will also be a holomorphic map. And then you will see that the limit again lies in here. So that will show that your space is actually compact. So now these spaces were an ingredient to state the main compactness result. I should just point out that because the proof here is given by this very explicit Arzelà-Ascoli argument, we can actually make this very effective. Given any epsilon bigger than 0, I can tell you how many epsilon balls in the Hausdorff distance it takes in order to cover this moduli space. So this is a very very nice metric space whose compactness I can understand in a pretty concrete way. That is, given any epsilon, what's the size of an epsilon net in this metric space?
Yeah, and can you also sort of get some control on the topology of the moduli space? I mean, say basically, if you say that this much part of the moduli space, if with some effective bound, say if you have some epsilon, then this much part of the moduli space is necessarily contractible, and you get some Betti number bounds of the moduli space. Is that possible?
So at the moment, I don't have any such very precise control. So, but yeah, I mean, that's something I still have to think about. But yeah, I mean, at the moment, I don't have any such result. This is just, I mean, at the moment, this is just controlling the compactness of this space. So just that very basic topological property in an effective way. I still have to see if, I mean, there is no general reason why the topology of these spaces should be very nice, except unless J is chosen somewhat generically. So yeah, I'm not completely sure.
No, I mean, this kind, what I'm saying, I mean, the kind of control that that this would give would be very sort of, I mean, typically it's something like you're going to get a nerve of this covering. And that's going to give you some kind of a simplicial complex.
Right.
The topology of that simplicial complex is going to control the topology of the moduli space. Typically, it's going to be rotten estimates.
Yeah.
So it's
yeah.
I mean, I'm pretty sure you get much better estimates outside.
Yeah. So to be completely honest, I haven't yet thought about this in that much detail. So yeah, it's certainly something I will try to think about. But yeah, I mean, right now I don't have anything very good to say about it. Okay, so now as I just argued, each of these moduli spaces, they are just moduli spaces of stable maps with a lot of decoration. So this decoration being this thick thin decomposition given by this tree T. So of course they have forgetful maps to the actual moduli space that we care about, the moduli space of J holomorphic curves of genus 0 in class beta. And so now let me get to the main theorem. So the theorem says that we can actually find constants theta and eta, which are just absolute constants independent of this homology class, and explicit constants lambda and n, which actually satisfy this kind of a bound, that n and log lambda are both bounded by the pairing of omega with beta, so that the images of these forgetful maps actually covers the moduli space, provided we let the tree T range over all stable trees with less than or equal to n leaves. So, so let me point out that because these trees are stable, once I bound the number of leaves, the number of trees is also bounded. Because as observed before, we cannot have this kind of just chain of spheres appearing, because that would violate stability, right? The degree of each vertex in such a path will be just 2, and so that will violate stability. And so such big chains are not possible. And so in fact, the number of leaves will tell us how many vertices and edges at most the tree can have. So that tells us that the number of such trees is finite. So in other words, so to parse this statement more roughly, what we are saying is that we have covered the moduli space m bar 0 of xj beta by an explicit set of compact sets, each of which we can sort of effectively understand its compactness. Namely, given an epsilon, we can understand how many epsilon balls it takes to cover each of those compact sets. And moreover, we can also understand how many such compact sets are there. And that's just given by the number of trees with less than or equal to n vertices, n leaves. So, so I just want to make a remark before proceeding that this is a result which resembles an earlier but somewhat weaker result of Gromov from 2013. And this is the archive reference for this earlier result. Okay, so yeah, so next I will try to sketch the proof. So maybe in the interest of time, I am going to omit some details and focus more on the maybe pictorial aspect of this proof. So right, so let's see, what do we need to show for this for the proof of this theorem? What we need to do is fixing any point in the moduli space sigma j u we need to show that there exists a tree T with a bounded number of leaves, such that I can endow my curve with this kind of a thick-thin decomposition modeled on T, and so that the resulting map, so that the resulting Lipschitz constant I have for the map, or in other words, the C1 bound for the map is actually bounded uniformly in terms of the original homology class beta. So in other words, given any random stable map, I need to produce a tree and a thick-thin decomposition for this and show a Lipschitz bound for that. Okay, so here comes the first key observation, which is that since omega tames J, this means that the energy of U is controlled by the integral of U upper star omega on sigma. And this latter thing is actually just a topological quantity, right? Because omega is a closed form. And so this is just the pairing of the de Rham cohomology class of omega with the homology class beta. So this is exactly saying that fixing beta gives us a uniform energy bound. And now let's recall that the mean value inequality, which told us that if the energy on a ball is small, then I can estimate the derivative at the center using something like the mean value inequality for subharmonic functions. This inequality can now be exploited because we know that there is a total amount of energy which is bounded. So we are going to divide our curve into small balls, each of which carries a small amount of energy, and estimate the gradient on each of those balls. So that's the rough idea. So let's make this a little more precise. So assume that sigma is a non-singular curve for simplicity, and fix any identification of sigma with P1, because of course the genus zero curve is abstractly P1. So at the moment, let's just fix any identification with P1 and write P1 as C along with a point at infinity, and let F be the corresponding map from C to X. So F is a holomorphic map, which is just the same as the map U, but using this identification of sigma with C union infinity. Okay, so now actually, how much time do I have? So maybe I will accordingly.
You have about 10 minutes.
10 minutes. Okay. Okay. So right. So maybe yeah. So let me introduce this main object and then maybe not go through all the details. So for each Z and C, let's define a radius R of Z bigger than 0 by the following requirement. Namely, R of Z is the distance you need to go from Z in order to capture an energy H bar around Z. So in other words, R of Z. So if you take bigger and bigger balls around Z, eventually you'll reach a ball where you capture exactly energy H bar on this ball. And so this will be some unique radius. And this is the radius that I'm associating to each point Z. And you can see that if the derivative is very large at this central point, then R of Z should be very small, right? Because somehow you need to go not very far out before you capture a certain amount of energy because the derivative is very big. And conversely, if the radius is big, then this should tell you that the derivative is small. And so more precisely, this is what is the third observation here, which is essentially the mean value inequality applied to this ball. So it's telling us that df of Z is smaller than or equal to a constant divided by R of Z. So constant times square root of H divided by R of Z. So this is just the mean value inequality that we noted before. And two other properties, which I will skip in the interest of time, just say that R is a continuous function and it has the property that it has a positive minimum on every closed subset of C. So, and this is basically because R goes off to infinity as Z goes to infinity. So in particular, it has a positive minimum on every closed set. Okay, so now, we need to find that collection of pink regions that was there in order to construct the tree T. The pink regions, before I tell you what they are, I would want to construct what their centers are. So this is exactly this portion of the proof. So I'm going to pick a set of points S, which are the centers of these pink regions. And these are picked according to the following algorithm. So basically what this algorithm is doing in words is that what it does is it first picks the point with the smallest possible radius. So this is sort of a greedy algorithm. So it first picks the point with the smallest radius, R of Z. Then it looks at all other balls whose radius R ball might meet this one. And it throws all of them out and then looks at the ball with the smallest radius which does not meet this original R ball. It puts that new point into S as well. So now we have 2 points in S so far. Now to find the third point, you ask, okay, is there any other point whose R ball is disjoint from the R balls of the 2 points we have chosen so far? If not, then you can stop. But if there is such a thing, then you pick the one with the smallest such radius. So this is basically some kind of this algorithm written down as a loop.
Yeah, you're constructing basically a net, right? A sort of a uniformly separated net, right?
Yeah, but I mean, somehow distance is not the criterion. The criterion is how much energy that it.
It's a conformal net. Yeah, it's determined by the energy, which in turn is right.
Yeah, so it's essentially like a net, but yeah, it's determined by the energy. That is, we sort of consider 2 points close if the R balls the R balls centered at those intersect, or more precisely, if you follow the algorithm carefully, the 2 R balls centered at them intersect. So right. So basically, the first observation is that this loop will actually terminate because we have finite energy, right? Because each of these balls has a certain threshold energy h bar, and the total amount of energy to go around is just E of u. And so there can't be more than E of u divided by h bar balls. So that's what shows us that the loop will terminate. And because we were picking these using a greedy algorithm, this tells us that for any other Z in C, you can find one of these bubble points S, one of these bubble points W in S, so that the radius at W is smaller than or equal to the radius at Z, and the 2R balls centered at these 2 points actually intersect one another. Okay, so now combining this with the mean value inequality. In the interest of time, I probably skip this and see that it's just a simple consequence of the mean value inequality that we get a gradient bound on F, which basically is governed by the distance.
So you will not get so the choice is made at each step. So you will not necessarily get it's not S is not the final output would not be a God-given set.
Yes. Yeah, I mean, you should think of this. I mean, it's an algorithm in the sense that I'm telling you the procedure, but the output is not sort of well defined. You need to
make this choice at each
Yes.
Okay.
Yes. So I mean, in fact, even the whole tree that I will construct is not canonical. We are just trying to show that a bunch of sets cover our moduli space. So I'm going to make a lot of choices, and as long as I can make those choices, so that
I see. So yeah, of course, a point of the moduli space might lie in more than one of these small. These are neighborhoods near the boundary, I guess. So.
Sort of, yeah. So so basically, I mean, there are a lot of choices involved. So we are just trying to prove that the moduli space is covered by a lot of these. Maybe a lot of these sets overlap a lot. So yeah.
Okay, thanks.
So right. So now we get a gradient bound, and the important thing I want you to notice here is that this gradient bound looks like 1 over the distance from Z to the bubble point set. So this is to be expected, because we cannot expect to get a uniform gradient bound on the entirety of the curve. As we've seen in the blow up example, this cannot simply happen because, I mean, we have examples where the derivative actually blows up. So we should expect that the derivative will blow up near some of these points. And so what we have figured out is a finite set of points whose size is bounded, right? We found that the size is actually bounded by the pairing of omega with beta divided by h bar. And we have a gradient bound that blows up near S, and we have this, which is of course the definition of R itself. Okay, so the important point here is remark number 2, which says that these 2 bounds are actually scale invariant. That is, if I actually zoom in to see, then and I transform F, S, and the set of radii R accordingly, according to affine transformations of C, then this bound remains intact. So this bound remains exactly the same. So this is a very good sign, because I mean, we should expect bounds which are more or less conformally invariant, because that's sort of the only canonical thing we have in the background. All the other things were just choices. For example, the identification with C is a choice. Okay, so now the rest of the proof is now going to be literally just a sketch, because the details are somewhat more involved. So we take these points, and so these blue points here in this green disk that the mouse pointer is over, These are the bubble points that we chose, the points of S. And now some of these points are closer to each other than others. So you should think of this as, if you have marked points on a Riemann surface, how do we compactify? We say that if they collide with one another, a new irreducible component sprouts out. So we are just trying to carry out this process in a more quantitative fashion. That is, I will have some precise quantitative condition for when I will group 2 points together. So I will say if 2 points are too close to each other, I will actually put them in a single cluster. So each of these pink regions corresponds to points which are sort of far away from everybody else to deserve their own cluster. Whereas this is a pair of points that are very close, so we put them in their own cluster. This is a bunch of 5 points which deserve their own cluster. And now we zoom in further and we sort of inductively proceed. And so because of the remark I said earlier, that these estimates that we have are scale invariant, we can sort of carry over the gradient estimate to each of these zoomed in small balls as well. So here you can see that there were 2 points which were very close to each other, which got separated in the zoomed out version. And now by dividing our curve into clusters like this, we get all these regions that I color according to this, namely that each solitary cluster gets the pink color, each annular region gets a red color, and all the remaining stuff gets a green color. So we form this tree inductively by rescaling again and again each time we have points coming too close to each other. And so the last thing I need to tell you for how to derive the gradient bound here is that obviously away from these bubble points we have a gradient bound. But as I get very close to the gradient to the bubble points, I know the gradient blows up. And so what should I do there? Well, there the mean value inequality again comes to our rescue, because this small ball, this pink ball, actually contains energy equal to h bar. So I can again use the mean value inequality to determine the gradient near the origin. So we can have the bound which is actually blowing up as I approach the bubble point. I just disregard it near the bubble point itself and just simply use the fact that near the bubble point there is a controlled amount of energy, and again bound the gradient there. So yeah, I realize that this part is somewhat sketchy, but hopefully this picture of rescaling inductively is somewhat suggestive. And I mean, I can try to maybe provide more details in the questions if people would like to see. Okay, so finally, I'd like to end with an application which is in progress. So recall that if x omega is a symplectic Calabi-Yau threefold, and x, what this means is that x is a 6-dimensional symplectic manifold and C1 is 0, then its Gromov invariants are a collection of numbers n, g, beta. So for each genus G and each homology class beta. So then there is an open question which asks, how does ng beta grow with the pairing of omega and beta? So in other words, more analytically phrased, how does the Gromov invariant grow with the energy of the curve? So is there some kind of growth bound that we can give? So there is no known answer in general. There are specific cases where this can be answered, where the Gromov invariants are completely computable because of some kind of symmetry or certain algebra geometric techniques that are applicable in cases with a lot of symmetry. And there you can actually figure out that these Gromov invariants can be fit together into a generating function, and you can even show that it has a positive radius of convergence. So that gives you some very good bounds in those cases. But that's a pretty small class of examples, and we don't know any answer in general. So here's a possible approach on how one might try to do this in genus 0. So I will end with this. So suppose beta is a second homology class, right? A to be the pairing of omega and beta. So let's right now operate under the fiction that m bar 0 of xj beta is actually a finite set of points. So it's actually of literally dimension 0 and not just expected dimension 0. Then near each of these points, we can actually try and use the inverse or implicit function theorem to figure out a quantitative estimate for the fact that these points are isolated. Namely, we can try to find out an epsilon so that each of these curves is epsilon isolated, meaning that no two such curves are within epsilon of one another, right? If this is an isolated set of points, such an epsilon does exist, but the idea is that you would want to do this effectively, given that on each of these curves, you have these effective bounds that we showed in the theorem before. So, so this is the step 1, and step 2 now.
Just a quick question. Since you are talking about counting, so you are looking at the cases when actually the moduli space is of dimension 0. So in that case, wouldn't your forgetful map from your curves with all these what you call these trees, etc. I mean, essentially everything would amount to different choices of the data, right? The fibers.
Yes. So it would be sort of a massive overcount, but it's still just an upper bound. It's not an asymptotically precise estimate.
No, but wouldn't the fibers be positive dimensional? So I don't know. So
sure, but so that's where I want to come to step 2, where I'm not. I'm not counting the things in that set, but rather just noting that. Effective compactness just tells us that the number of points which are each at distance epsilon apart from one another has to actually be a priori bounded because a moduli space is compact, right? And this does not care about the positive dimensionality of the fibers. Maybe it gives us a very bad bound because the fibers are positive dimensional. But here I'm just saying something about distances.
Okay.
Right. So what I'm saying is that so step 1, we first try to find an epsilon so that any two curves within the moduli space are at least epsilon apart. Then in part 2, I use the fact that I have an estimate on the size of nets in the moduli space to say that estimate the size of an epsilon over 2 net in the moduli space. Then this is a bound for the number of curves there are, because I know that any two curves are at least epsilon apart. So this will allow us to actually find possibly a very crude estimate for the number of embedded curves. But at the moment, I think even a crude estimate might be good because there is no general result known. And we could, by going through this proof, making sure that we are doing everything effectively in A. So for example, step 2 has been done effectively in A. Step 1 is somewhat a fairy tale because the moduli space might not actually be of dimension 0. So that's what the next page is about. So there is a serious technical difficulty, which is, as Professor Ramdas pointed out, the moduli space might not actually be 0-dimensional. So it might not be smooth of the expected dimension for the given J. And so there are two possible approaches we could take. One is to perturb J generically so that the moduli space actually consists of isolated submanifolds. So it's actually true that we can't always get them to be isolated points, but at least we can get them to be isolated compact submanifolds. And then try to estimate stuff in this case. So this seems a little bit difficult because it's not clear how to do step 1 uniformly in this case. That is, do step 1 explicitly depending on just the energy bound, because this will need some kind of careful argument with some kind of quantitative Sard's theorem. So this is something which might be possible, but at the moment I'm actually trying the second approach, which is try to use some version of virtual fundamental classes. And so virtual fundamental classes, in a word, are just a way of doing intersection theory without perturbation. So what we do is it's the analog of using Euler classes defined as the pullback of a Thom class. So that's the definition in algebraic topology, which does not require transversality, versus the definition in differential topology, which requires transversality by saying perturb the section so that it becomes transverse to the 0 section and then count up the zeros with multiplicity. So virtual fundamental cycles are to actual counting as the algebraic topological definition of Euler classes is to the differential topological definition of Euler classes. So at the moment, I have some kind of explicit vector bundle setup so that this moduli space is cut out as the 0 locus of some explicit section of that vector bundle. And what I'm trying to do right now is analyze that setup more carefully so as to be able to estimate the relevant Euler class to get the estimate for the Gromov invariant. So yeah, so this part is very much in progress. So I am afraid I cannot say too much more in terms of details after that. So yeah, so I think I will stop there. Yeah, thanks a lot.
Thank you, Mohan. This is lovely talk. Yeah, and yeah, so do people have questions? Yeah, I wanted to ask something. You have this this collection of trees which is giving you the combinatorics of these bubbles, right? I mean, so I mean, if you see the thing that it reminds me of is essentially that the usual moduli space has this combinatorial structure, which is given given by basically the core, I mean, basically by fat graph. So, I mean, or Feynman graph. So, I mean, I don't know whether you can actually look at the part of the moduli space which corresponds to a particular combinatorics dictated by a tree. That might actually give you sort of, I mean, essentially, can you say that that your moduli, this whole big moduli space, is actually covered by charts which correspond to trees of a particular kind? Yeah, I mean, essentially, so you'll have to look at all marked trees with, say, n leaves, and then stratify according to n, and then again, I mean, right? So that might give you sort of some kind of finer control, and then that gives you a kind of chart, and the stuff where you have, I mean, this non-uniqueness essentially boils down to, I mean, this would be sort of a pipe dream, that two of these charts actually intersect according to, I mean, so basically there'll be, it decomposes your moduli space into open neighborhoods, and then these open neighborhoods indexed by the combinatorics of the particular tree, and then two of them. Yeah, so I mean, there might be a way of going from one tree to another by some move. This is the kind of stuff that one does in standard moduli space. It looks as if, I mean, it's sort of tantalizingly close. Your stuff looks tantalizingly close. And then there are these bits where there's non-compactness that's arising. I don't know whether this is a true picture or not, but it looks.
So maybe we can I mean, talk more detail afterwards, because I would also like to know exactly what you're saying in more detail.
Sure.
Yeah.
Any other questions? I shouldn't have. Okay, so if not, I mean, let's thank Mohan for this lovely talk.
Yeah, thanks.